it's just good afternoon. Welcome to you who are joining us today. It's a lovely sunny day where I am, so hopefully it is with you. If you'd like to share where you're sitting or where you're working from and who you are, that would give everyone else in the room a good dimension of what's going on. So today we're going to be running, as we often do, a poll beforehand. So the poll questions we'll run through in a minute. So you probably need to know, if you don't already know, how to get into the poll. Two ways. You can use the QR reader, which is sitting on the right of your screen, or you can go to www.slido.com and you can enter today's code, which is LM080722, which is today's date. So if you'd like to sign in, what we'll start doing in a minute is we'll run through the poll questions, that it will be on your screen, and we'll get going today. So just wait a moment or two for other people to join us. So we'll start going through the poll. So the first question, do you deal with any complex optimization problems in your company? Simple, yes, no answer. Two people have already completed the whole poll. So if you'd like to sign in to the poll and start answering, that's fine. Don't feel you have to answer it now if you don't want. We're going to run through the poll after Benazir's talk. So please do not rush if you don't want to. I'm sure Benazir will be quite happy to get your feedback then. Which methods do you use to solve complex design problems or processes? Now, I think here it can either be manual or digitization, but be interesting if you can share which method you do use to solve complex design problems or processes. And last question, do you use any optimization models, e.g. GA, CP, etc., to solve any problems? A simple yes, no answer. So I'll let you carry on answering those. We're going to be using Slido, as we always do, as a means of taking questions. So if you have any questions for Benazir, please do put them, if you can, into the Slido Q&A box. Now, if you think a question that you see and read is similar to the one you would ask, if you think it's a good question, you can thumbs it up, which means that question will come to the top of the list. I think we'll now start. So what I'm going to do is hand over to Benazir, let him introduce himself. Thank you for joining us today, and I look forward to listening to and learning, for me,
Thank you very much. Thanks,
and to the case studies. Thank you. Over to you.
Thanks, Howard, and good afternoon, everyone. First of all, I will share my screen and okay. All right. Yeah. Can you see very well? I hope. Yeah.
Super. I can see it. I'm sure Excellent. Everyone else can. Thanks very much.
Yeah. I'm Benazir. I'm professor in digital architecture at Nottingham Trent University. I'm architect by training, and I did an MSc and a PhD in artificial intelligence, actually in computer science department, where my work is mainly or was mainly focused on developing optimization models to automate design processes. But I work as well, and the last few years in different areas such as building information modeling, digital heritage, using VR as well in construction, in architecture and construction, in different areas in digital architecture. The talk I'm going to do today, it's I would like to through three case studies to show you examples of automation and optimization methods used in design either in, as I'm going to show, in building services design or in space layout design, or simply to deal with problems of emergency evacuation in buildings, etc. I think that the last few years, we have seen more and more the use of artificial intelligence in design, and I think this is growing and going to grow within the construction industry for the next coming years. Then my talk will be on 3 case studies. The first one, I will present a project we have done a few years ago on automating. Sorry, that's the first project that was quite recent. I mean, just before COVID. As I am also visiting professor at Huazhong University of Science and Technology in China and Wuhan, precisely. We have done this project just before the COVID. It's about optimizing emergency door location to minimize evacuation time. In the case study here is a museum. The second project I will present is a development of prototype which automate the design of building services. And in this case, it's fine core systems in buildings. And the last project, this is a very well-known problem in digital architecture, is space layout planning, automation of space layout planning. I will talk about it. This is quite old project, but I thought it's quite interesting to present it because I did this project 20 years ago, the last one, the third one. But it's quite interesting to see today we can use this for quite interesting applications, possible applications, which I would like to share with you. The first project dealing with optimization of emergency doors. In China, that's a couple of years ago, the department I worked with suggested me that there is an industrial problem in construction. There were a museum of Wuhan being in process of being built. Then the main structure was already built. And they checked on plan and they did some simulations for evacuation time in case of fire. And they found out that the time is quite high. And this is quite a huge building. It's 70,000 square meters. Basically, it is divided as the plan here on the right down side. We have 7 different safety zones. Then each zone is separately and each zone is worked out separately. Then they asked me if there is a possibility to minimize the time of evacuation in case of fire. Now, the only flexibility we had here is to be able to change the door locations within the different zones. Now, following that, we have developed a methodology first, what we have done first, and my presentation will focus mainly on this zone, but we have done the work for every zone. Then we have first run a crowd movement simulation using different models to see roughly what is the evacuation time as it is. And then we have used a technique called constraint-based design, which is a technique between artificial intelligence and operational research, which allow you to model a problem using constraints. We can use some optimization models which allow you either to maximize or minimize some variables. Okay, then we used that technique to first represent the circulation of the building using a graph and to minimize the paths while changing the door location. That's the approach we have used. And to validate our solution, we have run the same crowd movement simulation with the new solution to compare with the previous one and see if we are improving or not. Now, this is the first, the plan of the first zone. And this is the existing evacuation path. We have 2 a safety zone, one on the top left and one here down right. And the public can evacuate either in either both different zones. Then from this, we have generated a graph representing the circulation of the existing solution. That's the first thing we have done. And the graph representation is mirror very well the circulation in this case, and offer a great possibility to use a certain technique in artificial intelligence, which are based on a graph theory, basically, on the mathematical side. Then we have developed a constraint-based circulation model. Now, what is the difference here is that every door, the doors are indicated by the D letter, which correspond to the nodes, and the arcs correspond to the circulation, the distances. Then the doors are characterized by a location XY within the space of the building, but each door here is characterized by a coordinate point which allow them to be on any position on the wall. Then the XY coordinates are a domain of possible values, okay? And it's not a fixed value. This is what we did. And then we have generated using optimization model, the location of these doors, minimizing the distances using constraint-based design. In fact, the distance of evacuation. Now, the first simulation work we have done on the existing solution, this is the simulation work we have done. We have tested the existing building as it is using different models. This is just one example where we have a combination between children, adult, elderly, with the different velocities as well. And we have used a software called Anirogic, which is a crowd movement simulation tool using agent-based system. It's a quite powerful system. Then we can really model different behaviors, etc., within the crowd, and which will affect the movement. But basically, for this example, we needed around 328 seconds to evacuate the building. I think it is around 400 people for this particular example. Okay, that's for the existing. Now, following the generation of our new solution using constraint-based design, the door location changed slightly, either up or down, etc., or move more. Then the new location of the door allowed to minimize the path evacuation time within the building. And we have run the same simulation using the same models as we have used with the previous solution, and we compared with. And this is quite interesting comparison graph. The red line is the time evacuation for the original layout. And the dark one is the new solution which we generated using our optimization models. We see that we have people, more time saving of evacuation we have. It's quite interesting to see this model. And this model include pedestrian or include building occupant from different ages and nature. Okay, there is a mixture between children, elderly, etc. But when we have run as well other models here, we see that as well we save a lot of time evacuation, but the time saving here is quite nearly constant. In this case, we have used the same type of pedestrian, only adults, with the same velocity, 1.2. And we see in this case, effectively, we have the same time saving, nearly whatever the number of the occupant we have. It's quite interesting to see, to learn, to see these differences which are affected by the type of people you have, the velocity of these groups, etc., which affect the time saving you have. But overall, we have saved quite substantial time. If I go back to this one, for 500 people, sorry, we have saved around from 328 seconds, as I said before, to around 240 seconds, which is quite a good saving, more than a minute of saving for evacuation time. Then it's quite an interesting technique to use in this type of problems. This is the first example I want to show you. The second one, it's we developed a prototype which is embedded in a BIM software microstation from Bentley System. We developed our own algorithm which interface with MicroStation to automate the design of building services, in particular fine core systems, which include diffusers and pipe and duct routing as well. In this slide here, we have on the top left, we have a solution on both slides here, it's examples of solutions, fine core system designed by engineers. In this case, we worked with AECOM as partner, and this project was funded by EPSRC, which is the Research Council funding body. This is examples of solutions provided by the engineer in building services as they do traditionally, okay? In our case, I show you here on the bottom right, example of solution in 3D generated by our system using BIM platform. And we see that mostly engineers usually solve this problem in 2D. Then I will come back to that anyway. Now, just to, before going to the methodology we have used and different stages to develop this system, I would like to show you a demo of the system here, just to give you an idea. I think I need to go to more, optimize for video clip, yeah. Yeah, this is a 3D model, BIM model from MicroStation. After several inputs, the system generates in 3D, calculate first using rule of thumb, number of fans, diffusers, etc., and then locate in a 3D space all the fan coil systems and diffusers automatically as a first stage, dividing this building, which is H-shaped, in 3 zones, 3 rectangular zones. And I will come back to that as it is very important to divide any complex geometry in much more simpler one to solve the problem. Then after locating automatically all the equipment in 3D space in a sailing void, the latest stage will include the pipe routing, duct and pipe routing. Okay. Then I will move it slightly further. Yeah. Now we see the generation of this pipe here. Now the system starts by generating the main pipe is between the riser, and we have 3 risers in this building, between the riser and the farthest fine coil, and then generate the secondary pipes and duct between the main pipe and the fine coils, as well as between the fans and the diffusers. Okay. Then this is basically what the system can achieve. And that can be done in 3-4 minutes of time. Now I go back to my slides. Now, how have we achieved this? Basically, we have used a hybrid approach, which is again a combination of two artificial intelligence and operational techniques. Case-based reasoning, that's the first technique, and constraint programming, which we have used in the problem of the evacuation time. Now, case-based reasoning is a very interesting technique. It's a technique which allows you to basically develop a knowledge base which help you, if in the case you have a new problem, to use that knowledge base to solve new problems. And this really mirrors very well the way designers, building engineer, or building services engineer practice. Basically, if they have a new problem, they see if there is something similar which has been done and they try to adapt it. Okay, and mainly if they have 2D drawings in CAD, it's quite easier to copy and paste, try to adapt what you have already done in a similar buildings. Now, case-based reasoning, the approach, you need to develop what we call a case library, then a set of solutions which you have done previously. And then if you have a new problem, you will check in that case library if you have similar problems which has been solved before. You take that solution and you try to adapt it in your new problem. Okay, this is the basic of the solution. Now, the adaptation to that problem, we use constant programming, and I will tell you why. Now, for the case library, we have developed with IECOM actually, and the Biddle system, which were partners as well with Bentley system, a standard solution library, which is basically a set of solutions which are based on a different criteria, such as, I talked before that we divide building by zones, then by the shape or geometry of the zone, by a regular polygon, which is a rectangle or square. This represents 80–90% of our building. Then it's quite very representative. We have developed cases for polygonal shape, for circular shape, etc. That's a different case solution we have developed. We haven't developed, for example, for much more complex, I come back to that, geometries such as curved, for example, facade, etc., which was quite complex to model using this approach. And each case will include the different design rules to calculate or to the number of fans, the number of diffusers you need for that solution, and use a certain way of allocating in the 3D space those different equipment. For example, for the rectangular shape here, we use just a grid to locate our different equipment. Now, when I have, for example, a square problem building, okay, and I retrieve a solution for a square and I adapt it, the solution will not be 100% good because I just use a grid and put my equipment there, okay? What will happen, and this is where case adaptation come in force, I will have a lot of super problems, such as, for example, overlapping between a fan coil and a structural element, column or beam, whatever, okay? Then the first stage, we put all our different equipment in the 3D space based on the way they should be there. And then we check if there is any inconsistency or clash detection, if you want, to see if there is any problem, such problems. And we solve each problem separately using non-overlapping constraint we have developed using constraint-based design to give it the right location, ensuring that there is no clash and no problem, and ensuring that there is a minimum as well, a space around that equipment for maintenance, etc. Okay, then and the interest here is that by looking at each problem separately, it's very good in any optimization process, because one of the limitation of the optimization models is the size of the problem you are dealing with. Smaller the size, the better it is, and more fast, more quicker you can get a solution. Now, if I take all these problems as a whole, as one problem, it will be very timely. Then this is why we prefer to solve them separately, and that can be done in a very reasonable time. That's the first stage. And then we can get, as I showed you before, the location of our fan coil systems with their diffuser within a sailing void of the building, meeting all the technical requirements of solution. And even our solution, as we have worked with Biddle Air System in this project, we can export all the information to the supply chain. Basically, we know how many equipment we have, what type of equipment, what type of fan coil, etc. And that could be very useful for the following processes. And this is an example of a first solution we can have. And you see here, for example, this is not in the same line grid as this one, because there were certainly a problem and has been moved forward thanks to a different constraint after checking the first solution. The second stage is the pipe duct routing, which is a very complex problem. We are working in this area for years. And in this case, we haven't used case-based reasoning for pipe routing. We have just used constant programming directly. We have three types of ducts, for this problem. I said that the main one, riser to the farthest fan, and then the secondary. We developed a knowledge model for our pipes. Then each duct or pipe is defined by the number of bands, segments, and orientation. The number of bands, it's a constant base variable. Then it's a variable which have a domain of possibilities. That allows us to use the constant based approach to optimize the problem. Then with the algorithm we have used to generate a solution, for example, if we look at this here, that's the riser, and we select the farthest fan coil to generate this pipe. We used heuristics to help the system to search for a solution as quickly as possible. Okay, and that heuristic has very much based from some time of common sense, your experience, etc. Then in this case, we know that looking at the position on the starting ending point, we can't have one segment, we can't have two segments of our duct. Then we straightforward start to generate a solution with three segments that will allow to the system to very quickly test and the solution with three straightforward. Then we don't, and the time response will be quite low. And obviously we will use non-overlapping constraint to make sure that the pipe doesn't pass through any. Now, if there is a middle obstacle in the middle, for example, here, we can always imagine there is no possibility for three. The system will check then with 4 and with 5 and with 6, etc. Now, the heuristic allows to look at the topology of the existing to help the pipe routing algorithm to choose the number of segments from the beginning, which could be close to the solution, just to reduce the response time. Okay. And this is examples of the output we had on the system. This is from MicroStation, where we use it to display the solutions in the BIM model. Now, we have benchmarked, we have tested these solutions with our partner, AECOM. This is an example of building we have used in benchmarking exercise. What was great is that we have tested building which has been done in the traditional way by AECOM, and to see the difference in design. Then we have get as well some qualitative analysis of the solution by the engineer of ICOM to tell us what they think about the solution, what is good, what is not, what should be improved, etc. Then just quick for response time. This is for the pipe duct solution. I have this result. This is the latest work we have done. That's, I think, i7 Pentium 3.4 or 5, I don't remember exactly, but that give you at least an idea of a time response of pipe routing, around 2 minutes, basically, to generate, if we add up everything, around maybe 3 minutes in total to generate the pipe and duct for a solution I have shown you. This is a feedback from the engineer. To summarize the feedback, I think the main element is that the solution we have provided were technically ticking all the boxes, but they were not 100% what the engineer wants. But that was quite interesting because we had the issue of the heuristic knowledge, the knowledge the experts have through their experience, which we haven't modeled, we couldn't model in this prototype. Then pushing slightly a pipe because of something could happen, etc. I mean, there is a lot of knowledge which is very important to improve the solution. Then from that, we decided to provide to the engineer an automated solution as we did, but a parametric one. Which means that, for example, this is a nice example of a pipe which meets all the criteria technically, but the engineer wants it in the middle, okay, between here. Now, while providing the parametric solution, just by dragging routine, the engineer can pick this pipe and moving up, and the whole solution is redeployed automatically. This is thanks to the model we have used. Behind every solution we have here, we have a graph of constraints. Okay, it's not just a list of objects. We have a graph of constraints where we record all the geometrical relations, etc., between all different elements. Then if we want to move something, we click on, for example, the find call here, move it, it will redeploy all the different duct between the diffuser and the find call automatically, while meeting all the technical requirements, okay? And that's yeah. Now, following this work, we did work with ICOM. We have worked on optimizing riser in tall buildings, just to have a minimum space area to minimize the space. We have done other projects as well in this area. Okay. And this is the second project. And now I go to the last one. It will be shorter. This is the project I said that was a while ago. It's about space layout planning. This is a very old problem. We started to work on this problem since the 60s. It has 60 years actually. Yeah, that's quite incredible. I did work on this, and this is an example prototype I developed where we can describe a list of spaces. Here we have, for example, floors, etc. And for every space, I give a domain of possible surface area, okay? And with min and max, if I want. And I can describe my design brief using a different constraint, adjacency constraint between spaces, orientation. I would like this space to be either on the north or the south or any place. I would like that my bathroom is near my kitchen, etc. Then you can describe, but behind every right-hand constraint we see here, there is a mathematical constraint which will obviously set this relation. And then the system generates a graph of constraint, all different objects, and we use generation algorithm to get all the layout plan, as example here, of my flat here. Now, what we generate here, it's the different topologies, okay? And I think better to show you here. Now, the different topologies is where we have a difference in the orientation between different spaces, okay? As here you have 9 topologies, you have 2 identical examples, but for each topology, we can do some geometrical optimization where we can minimize, maximize spaces, surface areas, for example, etc. Now, because it's not interesting for us to generate, for example, for the top left solution, 2 solutions where the difference is maybe 10 centimeter wide for the living room. There's no interest for that. What we want to see is really the different topologies where there is a minimum of a solution. Then this is an example I want to show you, which has a lot of limitations now. For space layout planning, we are limited by the geometry of we can use. Then the least complex is to use a square and rectangle. We can go for L shape, which will increase a bit the complexity, but there is no possibility today to use a very complex geometries in this field. And the problem as well is the size of the problem. If we go beyond 50, 60, 70 spaces, we start to have some limitation in getting the solution in a reasonable time. But that will lead me to the conclusion. Then optimization models, as I said, are limited by the size and complexity of the geometry. And so, as I said now, it's a real problem. But if you are dealing with such problem, the best approach is to try to divide your problem in sub-problems. Then you will have more chance to reach a good result. Space layout planning, even if is still now limited, but open up, I think, new opportunities in different areas, and mainly in modular buildings and prefabrication. And this is an area we are looking at it now, and we are very interested to see how we can use these different, sorry, these different techniques to use it in optimizing in modular buildings. Thank you very much, and yeah, I'm very happy to respond to your question. But before that, just I have here a list of references I published, and where you will have description of all this project in much more detail. Thank you very much for listening. I think I will. I can't hear you, Howard.
Thank you very much, Benashir. That was very interesting. I think we'll go through the poll that we have to see what feedback we get. So, Abraham, if you could please, if you could start with question 1. Do you deal with any complex optimization problems in your company?
We have 14%, yeah.
We have 14% who say yes.
Great,
yeah. I wonder whether the issue is complex optimization. I wonder whether that's perhaps what people don't understand. It's certainly something I don't fully understand. Could you explain complex optimization?
It's any problem which is a combinatorial problem.
Right.
Okay. If you have different variables, and you can have sometimes thousands of possibilities by combining different values of these different variables to get a solution. Right. Mathematically, we call it non-polynomial, but it's not interesting to go to this route. But it's problems we can't solve with a basic equations in mathematics. Then we need to use optimization for that. I take an example which maybe, for example, scheduling construction processes. Okay.
Yeah.
That's an optimization problem, because we have after and before, but we have parallel processes, etc. And if you do it manually, okay, you can get a result. But it's a very nice example of optimization using, and there are a lot of work done using constant programming actually for optimizing processes in construction. That's an example.
That would be used within a project, or would that be used in? Yeah. Okay, fine. That explains it more for the simple one like me. So thank you very much. Which methods do you use to solve complex design problems?
Yeah, that's interesting. Yeah.
Yep. Did you expect to get manual come back before anything else?
Yes. Yeah, I was expecting that. Yeah.
Okay, fine.
Mainly in the construction industry.
So, yeah, that's an interesting comment then.
What is extraordinary in the automotive industry, you will have the opposite.
Yeah, I mean, I have done some work over the years, and you are right. I mean, many years ago, they were looking to use, the early days of AI and that sort of thing. So do you think the construction sector or the building sector is behind catching up, or a long way to go?
No, it's behind, unfortunately. I mean, it's a fragmented industry, as we know. Then it is behind, yes. And we always learn, and we still learn from aerospace and automotive industry. I mean, that's a fact. We still talk about BIM, level 3, 2, etc. This is sorted out in the construction industry, in the automotive industry for years. Okay.
Yeah.
It's no longer a question. Then unfortunately, we are behind. Yes.
And I mean, you said at the beginning of your talk that you saw the next 10 years. Do you think it will take that long in the construction sector?
I hope not. I hope not. I think, I mean, the big companies are already adopting those technologies. I know, as if you see ICOM or you see Arab or others, consultancies or construction companies as well.
They're engineering companies, though.
Yeah, engineering companies.
As opposed to what I would call construction companies.
Yeah, absolutely. But I think it will come. Hopefully, it will come. Yeah.
What do you think the issues against it are? Do you think it's cost? Is it an understanding? How can it be sped up? I suppose I'm trying to say, is it more qualifications? What's needed?
I think it's understanding understanding the possibilities. The technology can offer. I think we haven't a good understanding on that, and that need to be really developed furthermore. I mean, as building information modeling with the BIM regional groups, which has been formed years ago, that was very nice way forward to develop the awareness of BIM within the industry, and I think now it's quite adopted, quite well adopted, much more than before. What was the social say?
Well, we'd have some questions. So the financial.
Yes, that's I haven't done any on the financial. I haven't done this work on the financial, but that's a very, very good, interesting question, because we have saved certainly on the engineer time without any doubt, because we knew that it takes around 3 weeks, 2-3 weeks to develop a full solution by engineer, where even with some improvement, the solution we provided, it could take maybe 1 day or a couple of days, but we haven't honestly calculated the cost or the saving in cost. No.
I think that might be, for the construction sector, a major consideration. The low margins that constructing firms work on, they're going to want to see the payback.
No, that's absolutely true. That could be a good motivating driver, the cost.
I think it would be. I mean, you're talking about, saving time in designing it, But if it's taking, that's a cost.
Yeah, yeah, absolutely. Yeah.
Okay. The next question then, please, Abraham. What format is the previous knowledge in, and how is it stored such that you can reuse it?
What format is the previous knowledge in? Okay. We used a Bentley platform, then we developed each case I showed you as a class, an object-based oriented class, okay? And we developed the different attribute, which are the variables defining the class, or the methods using constraint-based programming. And I remember we have used GNA, which is a Java native interface, to interface basically between the Bentley platform and the constraint programming language. But it was very much as classes within the Bentley platform. Did I reply to the question?
Well, the person who asked it, perhaps they can come back to us if he wasn't asked, but we'll move on to the next one. Is this work part of developing existing software capabilities, or is it an exercise in its own right that can be run in every project?
In fact, it was a research project, okay, funded by EPSRC, which is research council, as a research prototype. We were simply trying to validate to see if new artificial intelligence techniques could be useful to support a certain type of design. Now, automation is very important to say that it works very well where for the same processes you get the same result. In that case, yes, we can automate. If for the same processes you get each time different result, it's difficult to automate. And this is where I come back to architectural design, for example. If you put 100 architects for the same problem, you have 100 different schemes. Then that's where then this is why these techniques are very, very useful for much more building engineering. That's such as building services, etc. I think it fit very, very, very well for that. But at this stage, it's just a prototype which we have, and we would really love to see if someone from the industry can take it furthermore.
When you say from the industry, any particular part of the industry? Is the industry?
It need to be one of the BIM software developers.
Right. Okay.
Yeah.
Right.
Yeah.
Okay. Well, I don't think we have any more questions. Oh, hang on. As users, we would like the software we already buy to offer these capabilities out of the box. So there's an interesting one.
Yeah. Thanks for the encouragement. that's yeah, again, to put something like that in the market as academic, it's not our job. We can't do that. It needs to be really supported by big CAD BIM developer, unfortunately. Okay,
so just to look at that. So as a professor, you obviously have master's doctoral students under you.
Yeah.
Are
Yes.
any of these being funded by construction firms? In other words, are people in it? So is it going to get in there, or is it unfortunately going to be missed because it needs to be sold to them?
Now we had KTP with IECAM,
right.
Which funded. We took part what we developed here and we apply it for risers for tall buildings, again, for building services. We had a PhD studentship, industry funded PhD studentships as well. Then now we had some funding on that. But the time I'm talking now on this particular subject, I still have PhD students, but they are not funded by industry, funded by either NTU or by their own government as well.
Right. So that's something for the industry to think of.
Yeah,
Who,
hopefully.
who's
Yeah,
who's going to step out of the box and do something that's a bit different, a challenge for change?
hopefully. Yeah.
Okay. Thanks very much. If anyone does have any more questions, please lob them in. We have a few more minutes left, but we do have the feedback survey up. So if people would like to fill that in, that would be super. What we'll do now is we'll put up next week. We have a slightly earlier time. So Abraham, if you want to change, put it up there between 10 and 11. We're looking here at the Weymouth Seafront Master Plan. He's an award-winning designer, and he's going to discuss the plans for this one-off special in this one-off special webinar. So please look at the time. It's 10 to 11. It's a change from a normal time. So if you want to enroll with that, please go to leadersmeets.com and register today. If you would like to get a certificate for your attendance for CPD, you can go to MyProPass. I'm sure some of you have. You can create a free account and store all your certificates in one single place. So in terms of today, thanks very much for people attending. Any more questions, please put them forward. We don't seem to have any more questions, I don't think, Benachir. So I think what we'll do is we'll go for an early lunch if you're happy.
Thank you very much for that. Yeah, it was a pleasure.
Thank you very much. I found it very interesting, but I say I'm not in any way into the mathematics, etc., of the complicated AI, but it's a fascinating area, and I just hope it takes off for you.
Thank you. Thanks a lot. Bye. Bye, everyone.
Okay. Thanks for everyone, and hope to see you next week. Have a great weekend. Weather looks
Bye-bye.
super. Bye.